We're going to solve problem number 8 by finding the areas of the regions bounded by the given curves using any method, either horizontal or vertical rectangular strips, okay, using the curves xy square is equal to y square minus 1, x is equal to 1, y is equal to 1, and y is equal to 4. Again, the curves were already sketched, okay, assuming that you already knew how to sketch the graph. And the red graph is our x squared is equal to y squared minus 1, wherein when we express or rewrite in terms of y, okay, we have x is equal to y squared minus 1 all over y squared. And the green one is the x is equal to 1, the pink is y is equal to 4, and the purple is y is equal to 1. So the area or the region of the curves is this, and this is what we're trying to solve, okay? So we're solving for the area bounded by the given curves. So here, let's decide what type of method are we going to use here. So let's try analyzing. Okay, let's start with the vertical line. Vertical rectangular strip first. So here, let's try this. So let's use rectangular strip. Okay, there we go. So as we observe, now the rectangular strip passes through, intersects the graph, and the y is equal to 1, which is good. All right. Now, however, if we're going to observe, now there is another rectangular strip that we could create or construct. However, it doesn't or it will not pass through the given curve. So by using this rectangular strip, okay, so which means there will be two partitions that we are going to consider here. This partition and the other one. So let's try identifying the partitions. So either this partition, the left and the right regions, okay, if we're going to consider the vertical rectangular strips. However, let's try what will happen if we're going to use the horizontal. Let's see. What we're trying to do here is we're going to find a way such that it would be easier for us to solve for the area of this region. So let's try using the horizontal. Okay, using horizontal rectangular strip. Now again, this strip intersects the graph and the x is equal to 1, which is good. And let's try plotting or constructing a rectangular strip on the other parts. Here, okay, they're behaving the same way. Here, also, they're behaving the same way. So which means it's better to use the horizontal rectangular strip than the vertical, because vertical gives us two partitions of the regions wherein we need to calculate the area of each partition. But in horizontal, a rectangular strip, we're just going to compute one partition or one area of the region, which is the region that we're looking for, right? Okay, so now let's use the horizontal rectangular strip now. So let's consider this bigger strip. Okay, again, this is just a representation of our rectangular strips a while ago. Let's use this. So we have, this is delta y, okay, and this is our x, all right? This is our width, and this is our length. The length is equal to, since it's horizontal, we have the right minus the left, okay? The right equation and the left equation. So here, let's identify the left and the right equation. So the right equation is that's x is equal to 1, and the left equation, that's x is equal to y squared minus 1 all over y squared. Okay, so let's consider or let's identify the area of the rectangular strip that we considered. So that's delta sub area considering the one rectangular strip. So that's length times width, and our length is equal to, the length is right minus left. So that's right minus left times the delta y. And let's substitute the values of right and left equations. So the right is 1 minus the left is, okay, this, the y sub 2 minus y sub 1 over y squared delta y. All right, so let's use the Riemann sums. Okay, so that's the summation of all the rectangular strips. Okay, so that's 1 minus y squared minus 1 all over y squared times delta of y, and I is equal to 1. And so our height is here. So here, so let's consider this our I, y sub I. All right, okay. So now let's go to the next board to calculate the, okay, to express the Riemann sum. Oh, by the way, we forgot the limit of n approaches infinity. All right, so let's convert this to integral notation. So area is equal to the area of 1 minus y squared minus 1 all over y squared with respect to y from, okay, let's identify the upper and the lower limits. Since with respect to y, so therefore we're going to consider the y-intercepts. Okay, the y-intercepts of this and this, that's 1 to 4. Okay, since we're dealing with delta y. Okay, so these are the points of intersection, okay, or the boundaries of the graph. All right, so this is also 1 to 4, 1 to 4, and 1 to 4. So we will be using 1 to 4 as the limits. So 1, 2, 4. Okay, so let's simplify this. Okay, so we have the integral of y squared minus y squared minus 1 all over y squared dy. And this is from 1 to 4. And let's simplify. So we have, oh, this is y squared minus y squared plus 1 all over y squared dy. And let's continue here. So we have the integral 4 to 1. That's 1 over y squared dy. Oh, okay. So it became simpler. So 4, 1, y raised to negative 2 dy. All right, so let's integrate this. We have y raised to negative 1 over negative 1 to be evaluated from 4 to 1. Okay, so this becomes negative 1 over y, 4 to 1. Okay, let's solve that here since we have only a simple equation. So we have, this is negative 1/4 minus negative 1 over 1. So we have negative 1/4 plus 1 is equal to 3/4 square units. Therefore, the area of the region bounded by the, okay, by the curves is equal to 3/4. So this area is equal to 3/4 square units. Okay, and I hope we get the same answer.